Now, it's time for you guys to have a little bit more information, okay? We need to label some things. The quote-unquote x-axis, I know that we already talked about this, but the quote-unquote x-axis in polar equations is called the polar axis, okay? The origin is called the pole. I mean, think of it like the North Pole or the South Pole. If you threw in the lines of latitude and longitude, this is very much what it would look like. Now, let's look at this guy. This is theta equals pi halves. This, our quote-unquote y-axis. Now, think about that for a sec. Why is theta equals pi halves equal to the y-axis? Well, if we think about it in terms of points, right, r comma theta, what this says is that no matter what r you give me, theta is always going to be pi halves, right? So give me an r of 15. Okay, that's cool. I go out 15 and up to pi halves. Give me an r of negative 7. Well, that means I go down 7, right? Or, excuse me, I can go up pi halves and then down 7, right? Does that make sense? But what I'll end up, if for any value of r that you give me, I'm always going to end up somewhere on this line every single time. So basically, theta equals pi halves, or say theta equals, let me change the color of my pen here for a sec. Whoa, I don't want that. What is going on? Oh, I changed the color of my eraser. All right, let's say, for example, that I said theta equals pi 6. Well, what would that look like? Well, that just means go to pi 6 and draw a line through the origin. Whoa, what a badly drawn line. This would be theta equals pi 6. No matter what r you give me, it's going to end up somewhere on this line. Now, this is akin, think of this as the analog to rectangular coordinates or Cartesian coordinates of something like y equals 5. Well, we know what y equals 5 is, right? It's a horizontal line passing through, oddly enough, y equals 5. Why? Because no matter what value of x you give me, y is always going to be 5, so it's going to end up on this line. Versus in this case, no matter what value of r you give me, you're going to end up on this line. Isn't that cool? That's pretty fun. Okay, let's bring out the big fat daddy eraser, and we'll start over. Now, what we're going to do is, I'm going to give you some rules. Because remember, we've got theta equals pi halves. Let me put those labels back on. I probably shouldn't have erased those. Well, that's okay. We got time. I have this right here is the polar axis. This is theta equals pi halves. And then this right here is the pole. Now, before we do this, we're going to do this over here, but I'm going to put some rules up. And think of these rules as almost being akin. They're the polar analog of even and odd rules. Remember how useful even and odd rules were when we were first learning to graph functions? If we knew something was even, we could reflect it across the y-axis. If it was odd, we could reflect it across the origin. We did it with sine, we did it with tangent, we did it with cosine. Excuse me, we did it with all kinds of things. Okay. Think about it this way. Rule number 1. If r of negative theta equals r of theta, all right? In other words, this smells a whole lot like even, doesn't it? All right, if this is true, in other words, if I stick a negative theta in wherever I see a theta and I get the same thing back, then I have a symmetric with respect to the polar axis. And if you think about it, another way that I could write the polar axis, isn't the polar axis just theta equals 0? Right? All right, number 2. If, now this one's a little bit crazier, so you gotta bear with me. Now, if r of, now here you go, pi minus theta equals r of theta. So in other words, if I stick pi minus theta in, and I get the same thing back, then I am symmetric. Whoops, symmetric. You can think about why that is, too, with respect to theta equals pi halves. All right? In other words, if I stick pi minus, so grab a theta, right? So think of it, let's do this. So let's just call this thing theta. But then what I do is pi minus theta, won't that give me, pi minus theta is like reflecting this angle across into the second coordinate, right? So if I get the same value out, then that just implies that these two values are going to be symmetric about theta equals pi halves. So it's pretty intuitive to understand why that works, all right? Just as it's pretty intuitive to understand why this guy works. If I go up theta or I go down negative theta and I get the same value, then I have symmetry about basically y equals 0, in this case theta equals 0. Okay, last but not least, number 3. Now there's no pretty way to do, well, there's no pretty way to do this. If I sub negative r in for r, and I get original equation back, and I'm symmetric about the pole. Okay? Easy. Nothing to it. So why do we want to know about symmetry? Well, we want to know about symmetry because it makes our lives easier. So the first thing that I'm going to do is I'm going to look at this thing and I'm going to say, okay, let's see what r of negative theta is. Let's see if we can make our lives easier. Well, this is going to be 2 plus cos of negative theta. I know that cosine is even, so this is just 2 plus cos theta. So I know that this is going to be symmetric about the polar axis, right? I know that it's going to be symmetric about what we think of as the x-axis. So that's kind of nice because that means I don't have to work as hard. So if I go r and theta here, right, and I plug in 0, well, let's see. Cosine of 0 is 1. 2 plus 1 is 3. That's easy. How about pi 6? Well, the cosine of pi 6 is root 3 over 2. So this is going to be 2 plus root 3 over 2. Right? How about pi fourths? Well, this is going to be 2 plus pi fourths, right? Or excuse me, 2 plus root 2 halves. Right? How about pi thirds? Well, that's going to be 2 plus 1/2. So let's start putzing with these and see what happens. So I'm going to end up with 1, 2, 3, comma 0 when theta is 0, right? 2 plus root 3 over 2. Let's get a good solid idea about what this looks like. So second quit, if I go 2 plus second root 3 and then divided by, whoops, I got to push out, don't I? Divided by 2, where does that get me? So 2 plus root 3 over 2, that's about 2.87, right? So where were we? We're at pi 6, correct? So if I go to pi 6 and I'm going to go about out here. Ooh, this is a little crazy, 2.8. Okay, that's cool. And then what was my next value? It was 2 plus root 2 over 2. Ooh, I'm going to cheat and go second entry and change this to, whoops, let's see if there's an easier way. I'm going to delete that. Delete that. There you go, root 2 over 2. Right, so about 2.707. So if I go to pi fourths, I'm going to get a little bit closer down in here. Right, that thing wants to bother me. So 2.7. Even dealing with this is a little bit tricky. So, but it's going to be right about in there. And then back here, let's see, when I was at pi thirds, I know that the cosine of pi thirds is 1/2, so that's just going to be, what, 2.5? So I go up here, pi thirds, 2.5 gets me right about there. So what's going on here? Let's look at pi, what did I get to next? At pi halves, Pi halves. What's cosine of pi halves? It's 0, right? So this gets me to 2. So that takes me back to 2 over here. 1, 2. That's crazy. Let's have a look-see. So I know that whatever it's doing here, it's also doing here, right? Just because of my symmetry. Ooh, that's a badly drawn graph, you guys. I'm sorry. It's also doing here. All right? All right. Now at this point, do we want to look at this? I mean, we've sort of wrapped our brains around how this thing works. Well, you know what? Let's get into the negatives and see what happens. That might be fun. How about at, what, 2 pi thirds? 2 pi thirds. Excuse me. I know that this is going to turn into 2 minus root 3 over 2, right? At 3 pi fourths, I know that I'm going to end up with 2 minus root 2 over 2. At 5 pi 6, this is going to end up being 2 minus a half, right? So let's see what happens with those. So now I want to go, oh, watch this. You'll like this trick. Second entry, and then I'm just going to change the plus to a minus, and we'll see what happens. So let's see. That was at 2 pi thirds. So when I go over to 2 pi thirds, I end up, that's here, I end up with 1.13. So that's 1.1. That's not very much. So this is going to swoop in like this. Wow, that's crazy. Interesting. Let's keep looking. I forgot to put in 2 pi too, didn't I? At 2 pi, what's cosine? I know that cosine is, or excuse me, 2 pi. I did it again. At pi, what's cosine? Well, it's -1. So 2 minus 1 is going to be 2, right? It's just going to be 2 minus 1. So what seems to be happening is this guy seems to be coming in right there. It's almost as though I'm getting like a heart shape. Ooh, that's bad. I'm going to redraw this other half because I can do better than that. That's not the best I can do. And since I want you guys to do the best you can do, I should probably do the best I can do. So, boom. It's almost like, woof. It's like a heart, isn't it? It's like a heart. That's really cool. All right, let's graph it. So y equals, let's go down. You know what, I'm going to have to clear that out anyway. Let's just clear it. And what did I say? 2 plus cos theta. Let's graph it. Let's see if there's a zoom. You know, my window might be crazy. Maybe not. Let's just look. Let's see what happens. Give it a graph. Oh yeah, my window's a little too crazy, isn't it? Okay, I need to tweak my window, so we'll back it out. And I'm going to go, let's go -3 to 3. Actually, I don't need, that doesn't matter. Let's keep it nice and boxed in. -3 to 3. And -3 to 3. Let's graph that. That's kind of hard to see what we've got going on here. Let's see if we can zoom in over here. Let me give me my window. Let's go X. A lot of this is just kind of playing with it, you know? It's kind of cool that way. X max, let's make our X max 4 and then graph it that way. Boom. Boom. Like that. Ooh, it almost looks as though I screwed up on the